So it's our third lectures for this course. I'm sure you are able to see the video of the past lectures in the course page. Are you able?
Yes, sir.
All right, better. So today we're gonna look at this is actually lecture 3, not 4. So we will try to assess ourselves. We try to see how you can understand some calculation using the kinetic theory of gases, which we treated last week. We look at how we can test your comprehension of the concept of the number density and other terms associated with the kinetic theory. Then understanding of the properties of ideal and real gas. I told you last week that there are some differences between ideal and real gases, and that the ideal gases obeys all the gas laws, but real gases do not obey all the gas laws. The real gas is what we are actually seeing, what we are using. The ideal gas is a model gas that used to model behavior of gas. So for us to be able to have actual equation for real gases, we modify equation for the ideal gases. So we have to comprehend the need for the modification of the ideal gas equation. That's we will look at the modification, and then one of the simplest and most common modification is van der Waals equation, and that is called equation of state. So we will look at this outline in the next 1 hour. So let's take one example. Calculate the average translational energy of nitrogen gas at 300 Kelvin. The average translational energy of nitrogen gas at 300 Kelvin. The first thing you need to know is what is the equation for calculating the translational energy. And the equation is 3/2 RT, where you have R is a gas constant, and the numerical value of the gas constant is 8.314 joule per mole per Kelvin. So you can now see that the gas constant is given. Then it means the translational energy will be 3/2 times R, which is 8.314 times 300. And the average translational energy is 3741.3 joule. So if you divide that by 1,000, that gives you 3.7413 kilojoule. So that is the average translational energy of nitrogen. Average translational energy of any gas can be calculated using the formula, finding that the translational energy is 3/2 RT. So that is the answer for that. And calculate the average translational energy of nitrogen gas at 500 Kelvin. Question. Yeah. So that's question. Calculate the average translational energy of nitrogen gas at 500 Kelvin. So that is it. Then the next one is calculate the average translational energy at 500 Kelvin. That degrees Celsius is not. It won't be the same. First of all, you have to convert the degrees Celsius. 500 degrees Celsius is equal to 273 plus 500 in Kelvin. The answer will be in Kelvin. We have to convert it to Kelvin. You know, we started with the SI unit. So most of your questions, when you're answering your questions, the unit of expression should be SI unit. So that gives us 773 Kelvin. So that is what it is. Now, let me try you with certain equation. The average translational energy of nitrogen is 3.74141 kilojoule per mole. Calculate the temperature that the gas has this energy. Can somebody try? Can you explain how you can calculate this kind of problem?
Yes,
Yeah, can you explain to me?
we can try.
Yeah, you can try. Try now. Try. When you try, after trying, we'll see if you really have the answer.
Okay. So, but what is the value of R?
R is always constant, 8.314. It's always constant, 8.314. Yeah. So let's work together. At least if you know, you know. So the average average translational energy is equal to 3/2 RT. Then that means that 3/2.
Yes, sir.
Madam, can you mute yourself? If you have a baby shouting, please mute yourself. It's better you mute yourself instead of us. Can you mute yourself? So that means the value here is 3.41. So when you multiply that by 1,000, that gives you 3741
741.
joule is equal to 3/2. 3/2 times
I'm just joining the class. I don't know how you get this. Yes.
the expression. The expression is the expression for, we are trying to calculate the translational energy of a gas. The translational energy is calculated 3/2 times R times T.
That's
Where you
the
have R,
formula.
yeah, that's the formula. R is a gas constant and T is the temperature.
Okay.
I'm not supposed to go back, but let me take you back to see. Calculate the average translational energy of nitrogen gas at 500 Kelvin. So you can see the formula is 3/2 RT. R is a gas, it's a constant. And that is 8.314 times the temperature. So in this next one, the average translational energy of nitrogen is 3.741 kilojoule per mole. Calculate the temperature that this gas has the energy. So you now recall the equation. You are trying to make T the subject of your formula. So in this case, your T, temperature will be equal to, please, who is carrying that baby? Mute yourself. I'll send you out of the class. Your T will be 2 times your T will be 2 times sorry, 2 times 8 point, your T will be 2 times 3741 in joule divided by 8.314 joule per Kelvin. Let's forget about the unit. 8.314 times 3 divided by 3 So we are trying to make T the subject of formula. So that's your answer, what your answer would take you to. Did you have it that way? Those who were solving, did you comprehend that same way?
Yes, sir.
Okay. So that is how to calculate it. So that's done for transitional energy. So that's done for that. To test yourself, calculate the translational energy of hydrogen gas at the following temperatures. So you can test yourself and you see what it looks like. I'll give you example for one. I'll give you the answer for one. Maybe I can even give you answer for so that you know, you test yourself and see if you are able to calculate it. So the answer is 3/2, 3 divided by 2 times 8.314. And that gives you 12.47. So the answer, the short way to have the answer will be when you insert that equation, you'll be able to have. So that means this will be 12.471 times 273. And that means the answer there will be 336.71712. You can try for yourself. So the next one will be 273. Sorry, 273. Sorry, that answer is not correct. The answer is then 3404.58312. The next one, the answer will be the answer will be 4651.683. So I'll give you answer for the two. Once you are able to confirm the answer for the two, the same method will apply for the other one. What is the relationship between translational energy and temperature? Already we have shown an example where we have the translational energy, and you see that the 3/2 RT is equal to the translational energy. So that you can now say 2 RT divided by 2 times the translational energy divided by R multiplied by 3 will be equal to the temperature. So since translational energy is 3/2 RT, it means the translational energy is proportional to the temperature. Since 3/2 and R are constant, the value of the numerical constant is therefore 3.2 times 8.314, which is what? That is equal to, let me see that is equal. The value of the constant is 3.2. The value of, that should be 3. Sorry, that should be 3/2, not 3.2. 3/2. That is 3 divided by
1.5 times
1.5. Yes, multiplied by 8.314. So that means the value of the constant is 12.471. So it therefore means to calculate the translational energy, just multiply the temperature by 12.471. If you do that, you have the answer. But if you don't know, you can go back to the preliminary status. So given that the translational energy of a system is 700 joules, calculate the numerical value of the constant. So what is the value of the constant? Numerical value of the constant. Let's say of the gas constant. Can you calculate it? Let's say the constant. Let's put it that way. The constant. The constant is this is a constant. Constant is the one you can express in value. So that's a constant. We have already calculated that. Given that the translational energy of a gas is 700 joules, calculate the temperature for this system. So we follow the same method we followed before. And this is our own result. So more questions. So that's more questions on the way. And we have number density. What is really number density? Number density is defined as the number of molecules of a gas per unit volume. The number of molecules of a gas per unit volume. That is number density, the number of molecules of a gas per unit volume. So we can say number density is the number of molecules of a gas and then the volume of the gas. We can obtain number density by rearranging the ideal gas equation. Now, look at the ideal gas equation. PV is equal to NKT. That is equal to RT. What do you mean by NKT? NK, where K there is equal to the Boltzmann constant. Boltzmann constant. Boltzmann constant. If you multiply the Boltzmann constant by the Avogadro's number, the factor is now R. So what we are using in effect is that PV is equal to RT. R is the same thing as saying, in other words, that means our gas constant R is the same thing as saying Avogadro's number multiplied by Boltzmann constant. That's the meaning of R. So we say PV is equal to RT and RT, or let's call it let's say we call it maybe let's use the first equation. We are using the first equation here. PV is equal to NKT. Let's use this one for N mole of a gas. So N is equal to PV all over RT. The number density is defined as what? Num N all over V. So we can now take V to be the other side. So that means N all over V from this equation will be equal to P all over RT. So this is an expression for the number density. This is the expression for the number density. The pressure divided by the Boltzmann constant multiplied by temperature. The pressure divided by the Boltzmann constant multiplied by the temperature. The Boltzmann constant is 1.38 times 10 raised to the power of minus 23 joules per mole or per Kelvin. That's the value, numerical value of the Boltzmann constant. So you can calculate the number density, which is the number of molecules of a gas all over volume. So that is the number of molecules of a gas all over volume. So that is how we can calculate that. So we now look at work example. Calculate the number density and concentration of nitrogen molecule at 298.2 Kelvin and 1.013 times 10 raised to the power of 3 Pascal. That's the pressure. The pressure is 1.013 times 10 raised to the power of 3. And you know from that formula that the number density is pressure all over Boltzmann constant times temperature. So the pressure is given here, and the pressure is given as 1.013 times 10 raised to the power of 3 Pascal. Then the Boltzmann constant, you know, is 1.38 times 10 raised to the power of minus 23. So when you multiply that Boltzmann constant with the temperature, you'll be able to calculate the number density. The temperature has to be introduced here. That's 298.2. So that will give you the number density. And we also know that the concentration of a gas is given as P over RT. When we talk about concentration, it's pressure all over RT. So now we can now see that P over RT, if we substitute that value, we have 4.086 times 10 raised to the power of minus 4 M. PV, that's C, concentration is P all over RT. What do you define by concentration? If you take the number of moles divided by volume, if you take the number of moles divided by volume, you have what you call concentration. So the number of moles divided by volume. Look at it, the number density can also be defined as the number of moles divided by volume. So you can also, from the number density, you can also calculate the concentration. Concentration is the number of moles divided by the volume. That's it. The concentration in mole per volume is also equal to the number density. So number density is simply the number of concentration in mole per volume. So that is what we call number density. Is there anyone that doesn't understand what we are calculating here?
Yes, I don't understand.
Yes,
No.
I don't understand it.
Okay. What is it that you don't understand?
The
Procedure
concentration
in
of the gas.
Eh?
concentration.
Everything
The
here.
concentration of the gas.
Yes, sir.
Okay, let me just open a chapter. I'm coming. Just a minute.
Okay, sir.
Let me open a new discussion. You know what is number density? Number of molecules of a gas divided by volume of the gas. Do you understand that one? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Yeah, you understand up to that point?
Yes,
Yes.
sir.
All right, let me take you from there. So number density. So we say that the number density is the number of moles equal to N all over what? Volume. You understand up to that point?
Yes,
Yes,
sir.
sir.
Then come to the gas law, PV is equal to NK. K is the Boltzmann constant. K
Okay,
is the
sir.
Boltzmann constant given as 1.38 times 10 raised to the power of minus 23. That's the value of the Boltzmann constant. You understand that?
Yes, sir.
Now, if you look at this equation, from this equation, we can say that N, we can say that our N, let me insert equation so that I can make it. Our N is equal to all over KT. Is that understood? How we get to that point?
Yes.
Yeah. So true that we can also write this equation as N over V is equal to P over. Is it correct?
Yes, sir.
Yes.
So what does this represent? When you look at number density, this expression for number density, and we have what base. You understand up to that point?
Yes, sir.
Okay, that is correct. Then we now come to another terms that we define concentration. As a whole divided by what? A volume. You understand that? You know that concentration is in molarity is of mole divided by volume. So we now say that the number density in mole per dm cube. You understand that? That is what we are doing here. So if you are given a formula here, calculate the number density and concentration of nitrogen molecule at 298.2 Kelvin and 10 into 3 Pascal. Pascal is the unit of pressure. Kelvin is what? That formula, number density is P over KT. So K is a constant, 1.38 times 10 raised to the power of minus 3. T is a temperature. T is the temperature. And then, so you can now substitute there, you are able to calculate the number density. And now, again, I say that concentration, the number density volumes. This is the concentration. The value here is also equal to the concentration. So that's what I have done so far. So that's what I've done so far. So mean square speed and root mean square. What is mean square speed and root mean square? Calculate the mean square speed and root mean square speed of methane. So the methane, the formula for methane is what? CH4. So carbon temperature is 514 Kelvin. So molar mass of this compound, methane, CH4, is 12 plus 1 times 4, which is 16 grams per mole. And that, when you are talking per mole, you divide it by 1 kilogram per mole. The mean square speed is given as, the mean square speed is equal to 3RT all over. R is a gas constant, and T is the temperature we've given here. So that is all over the molar mass. And so this is the mean square speed of that calculation. This is the mean square speed of that gas. That's the general formula is 3RT all over M. R is a gas constant, T is a temperature, M is the molar mass in kilogram per mole. Square speed is the square root of the mean square speed. So for that compound we just calculated, the root mean square speed is the square root of that values we add, and that is the square root of this, and we have the root mean square speed. So the mean square speed first, then you now calculate the root mean square speed. So second, that is what we have there. So now calculate the root mean square speed of hydrogen molecule at 500 Kelvin. Molar mass of hydrogen is equal to 0.002 kilograms. You look at the 3 times the temperature. The temperature is 500. R is a gas constant, 8.314. 8.314. Joule per mole per Kelvin. So now this is the value of the root mean square speed. The root mean square speed will be the square root of the mean square speed. So that means this is the square speed, and the square root is now giving you the root mean square speed. So that is the answer for that one. At what temperature will hydrogen molecule have the same root mean square speed with that of oxygen molecule at 125? This question calls for understanding. At what temperature will hydrogen molecule have the same root mean square speed with that of oxygen molecule at 128 degrees Celsius? So what is happening here is that first calculate the root mean square speed of oxygen. At what temperature would the hydrogen molecule have the same root mean square speed with oxygen? So calculate the root mean square speed of oxygen. Oxygen, the molar mass of oxygen is 16 grams per mole, divided by 1,000, you have 0.0016 kilogram per mole. So when you calculate that, and the molar mass is here, the temperature is 127. Once you calculate that, that means you are expecting the temperature that hydrogen will have this same root mean square speed. So now, this, you will now say the root mean square speed calculated is equal to 3RT all over M for hydrogen. So for hydrogen, you know the molar mass of hydrogen, and then you now find the value for the temperature. The temperature can be obtained when the root mean square speed is equal to this. That is that temperature for hydrogen. So, and that gives you, that root mean square is equal to 3RT all over molar mass in bracket. The molar mass is the molar mass of hydrogen gas. So that gives you that temperature will be equal to this. How do you get this? From here, when you remove the square root sign, you will square what is on the left-hand side, and this gives you here. Then make T the subject of the formula, and you'll be able to know the temperature that hydrogen will have the same root mean square speed with the oxygen at 127 Kelvin. So that that is how you get that self-assessment question. 1 times 10 raised to the power of 1 times 10 raised to, 1 times 10 meters cube. Let's say 1 times 10 raised to the power of 2 meters cube of a gas at a certain pressure and temperature took 151 seconds to diffuse a fuse through a porous barrier. How long will it take for the same volume of gas to fuse under identical condition? The mass of oxygen is 16. So what is given here is that you use Graham's law. You apply Graham's law. And what does Graham's law say? Apply Graham's law. And what does the law say? It says the rate of diffusion of all gases is proportional to the molar mass or to the vapor density. So that's what Graham's law of diffusion gives you. So the rate will be rate of diffusion will be volume of the gas that effuses all over the time, and you have gotten the rate there. So, and that gives you that the rate is now proportional or inversely proportional to the molar mass. So the rate will now be equal to about approximately equal to 1 over the molar mass. And that means the molar mass, relative molecular mass of the compound will now be given as 1 over the rate, the square of the rate, and that is what you have here. The volume of gas was 10 m cube. Okay. Sorry, I have to return that volume to 10 so that people don't get confused here. 10 meters cube. The volume was 10 meters cube. Yeah. So then the rate of diffusion of oxygen will be what? So that means the rate will be proportional to the molar mass. So you can see that is the molar mass of oxygen is 16. So that is proportional to the square root of the molar mass. So that means the rate, which is 10, the volume, which is 10, divided by times will be equal to this. And that means the time will be this. So that is how you can manipulate this type of problem. We can still move further to see how we can progress. A mixture of 2 times 10 raised to the power of 3 grams and 2 times 10 raised to the power of 3 grams of hydrogen and helium exert a pressure of 1.50 times 10 raised to the power of 3 Pascal. What are the partial pressure of hydrogen and helium in the mixture? The molar mass of relative molecular mass of hydrogen is 1, that of helium is 4. So now you see based on Dalton's law the Dalton law said that when gas that do not react chemically combine, the total pressure is the sum of the individual partial pressure. That means since helium and the hydrogen will not react here, the total pressure exerted by the mixture of the gas will be the pressure of hydrogen plus the pressure of the helium. So now you are asked what are the partial pressures of this gas. So now you now see that the total pressure exerted was 1.50 times 10 raised to the power of 3 Pascal. So that will be equal to the pressure of hydrogen plus the pressure of helium. Now we know something that pressure will be equal to nRT all over V. Pressure is given. If you look at the gas law, PV is equal to nRT. A partial pressure will therefore be equal to P is equal to nRT all over volume. So we can now see that the partial pressure for hydrogen will be equal to nRT. N is the number of moles. It was only 1 mole. So R is 8.314. And then T is the temperature all over volume. The volume is what? The volume was given here as 2,000 meters cube. So the same thing with helium, and the number of mole is 1. The gas constant is here, the temperature is here, and this is also given here. So now You were asked to calculate the partial pressure. So now PV, we have said that PV is equal to nRT. That means PV is equal to nRT all over 200. And that means we are able to calculate, we will see the common temperature. Once we see the common temperature, we will apply this. Name, let me, a mixture of this and this hydrogen at, let me put the temperature at 273 Kelvin, exactly pressure. So, okay, so now you can apply. So for oxygen, the partial pressure for hydrogen, when you multiply this by temperature, you have this. When you multiply this by temperature, you have this. So you will find out that this is a partial pressure for hydrogen, and this is a partial pressure for helium. So what is happening here is that this is a partial pressure for hydrogen. The partial pressure for hydrogen is given as and the temperature is multiplied by 273, and the partial pressure for helium will also be equal to this. Multiplied by the same temperature, since the temperature was the same, and that is 273. So that will give you the partial pressure. So that will give you, if you simplify that expression, you'll be able to have the partial pressure. You will be able to have the partial pressure. Now, calculate the ratio of mean square speed of oxygen to nitrogen at 300 Kelvin. The mean square speed. You know the mean square speed is 3 RT all over what? Can somebody remember that? 3 RT all over M. That's the molar mass. So calculate the ratio of the mean square speed of oxygen to nitrogen at 300 Kelvin. So now, first of all, let's see the mean square speed. Mean square speed of oxygen is equal to 3 RT all over M, the molar mass. So normally we're supposed to give you oxygen, the mass of oxygen and the mass of oxygen, the mass is what, 16. 16 grams per mole. And that of nitrogen
Is 14.
is equal to 14 grams per mole. $14 per mole. All right, so you can calculate the mean square speed here, and this will be equal to 3 times the gas constant 8.314 times what? The temperature. And what was the temperature? 300 Kelvin divided by the molar mass. So that of oxygen is 16 grams per mole. So you divide that by 1,000. So you have what? 0.016. 0.001.
Why did we divide by 1,000?
Because this one is given in gram per mole. The SI unit for molar mass will be what? Kilogram per mole. So you know 1,000 grams make 1 kilogram. So you divide by 1,000 and you are having that. That is the value for the mean square speed of the oxygen. So you now calculate the same thing for nitrogen. For nitrogen, you have what? 1.4 rather. Do you understand me? So the question now, calculate the ratio of the mean square speed of oxygen to nitrogen at 300 Kelvin. So you have calculated that of oxygen, you have calculated that of nitrogen. So what do you need to do? You carry the ratio, what the value you have here divided by the value you have here. That solves the problem. Now calculate the number, density, and concentration of oxygen at 1.013 times 10 raised to the power 5 Pascal, and the pressure of this. The oxygen is given here. So what is number density? Number density is N over V is equal to what? P all over what?
KT.
KT. K is the Boltzmann constant. So that is another one way about that. K is equal to 1.38 times 10 raised to the power of minus 23. So that is what you get there. So we have real gas, deviation from ideal gas. We have spoken that we try to make some mathematical calculation. I try to personally create time for this because most people find it difficult to handle mathematics when it comes to chemistry. So all gas obey all the gas law only at low pressure and high temperature. The condition that will make all the gas to obey all the gas law, that means real gas, ideal gas, is that they at low pressure and at high temperature. The gas laws are based on postulate of the kinetic theory of gases. They are based on postulate of what? The kinetic theory of gases. For ideal gases, the product of pressure and volume is constant. That means PV is always equal to constant. Why do you say so? If you say PV is equal to constant at a given temperature, that means the formula you know for ideal gas law is a PV is equal to nRT. So at any given temperature, the value of N is always can be the same. That's the number of moles. R is a constant. So the product PV is equal to constant for ideal gas. But for non-ideal gas, the product is not equal to constant. However, real gas show deviation from this law. Their characteristics or behavior deviate from what the perfect gas law should be. So the only way real gas and ideal gas will behave the same is at low pressure and high temperature. Outside that, there's a deviation. Ideal gas is hypothetical concept. The real gas obey ideal gas law only at low pressure and high temperature. So take note of that. It's a serious condition. So now let's test your understanding. Under what condition does the ideal gas or real gas, under what condition does real gases obey the gas laws? So what's the condition? So what are the conditions?
At low
Low
pressure
Low
and
pressure
high
and
temperature.
high temperature, yeah.
temperature.
So you see
At low and high temperature.
at a given temperature, the product pressure of and volume is equal to constant for ideal gas. It is always constant for ideal gas. So take note of those two terms. Reason for deviation. Why is it that at other temperature, that's when the temperature is low or when the pressure is high, there's a deviation. What we mean by deviation is that why is it that real gas do not obey all the gas law? Because they don't obey, that is deviation. Deviation means that they don't obey. So first, it is assumed that the volume of a gas molecule themselves is negligible compared to the volume occupied by the gas in the container. This is kinetic theory. That's the assumption that the ideal gas laws were established is based on the volume occupied by the gas molecule themselves is negligible compared to the volume occupied by the gas in the container. The second reason is that the assertion that there are no forces of attraction between them. So in real cases, gases occupy volume. The volume cannot be negligible. Another second case is that there's attraction. And because there's attraction, they cannot obey the law. Therefore, since the gas laws are derived using the above assumption, kinetic theory, which is not always true, except at low pressure and high temperature, deviation from ideality is often observed. This is why it is observed. It is observed, deviation is observed because they do not, volume occupied by gas molecule is not negligible. And two, there's also attraction between gas molecules. So behavior of real gases, the compressibility factor is defined as, so compressibility factor is Z. It's normally defined as PV all over RT. You know, the formula for ideal gas law is PV is equal to RT. So when you take the ratio, that ratio is called compressibility factor. For ideal gas, the compressibility factor is equal to unity. But for real gas, it is not equal to unity. If Z differs from the value of unity, the gas is said to deviate from ideal gas behavior and is a real gas. A plot of Z compressibility factor against pressure for several gas shows that all gases approach ideal behavior at low pressure because Z approaches unity at low pressure for all gases. Now let's look at such plot, how it looks like. If you see, this is real gas because the compressibility factor is 1, so it will go flat, it doesn't change. But this one tries to be at this low pressure. At this low pressure, it tries to show some closeness to this, but as the pressure keeps increasing, there's a deviation. So the compressibility factor, once it is 1, it is ideal gas, but if it is greater than 1 or less than 1, it's not ideal gas. So variation observed with temperature that's compressibility factor with temperature is the same thing. For ideal gas, it is parallel. But for this other one, it is not. It's not parallel. So that is what you see there. So summary, the deviation of a real gas from ideal gas is minimal when the pressure is low and when the temperature is high. As the temperature decreases, the deviation increases, and as the pressure increases, the deviation also increases. So that is this thing. Let's take a few questions. Calculate the compressibility factor for a gas. The following parameters: pressure equal to 100 Pascal, temperature is equal to 273 Kelvin, volume is equal to 22.4 dm cube, meters cube. And of course, you know the gas constant is equal to 8.31314 kilojoule a mole or kilojoule per Kelvin. Let's put it there. Can you calculate the compressibility factor? Is there anyone that can calculate the compressibility factor?
Yes, sir.
Z is equal to what?
Yes, you can try.
BP all over RT. So can you calculate it? Hence, state
I got
if
0.98.
if the gas, if the gas is ideal or real gas. So you say, well, your answer is what? Anyhow, let me calculate with you.
0.896.
Let me calculate with you so that we can be sure what we are right doing. 100 times what? P volume times 22.4 is equal to this, divided by R, 8.314,
8.314.
divided by temperature, which is what?
273.
You say, what's the answer? 0.
98.
69. So the
69.
gas is not ideal gas. Why? Why is the gas not ideal gas? The gas, probably, maybe if you take this is equal to 1, maybe approximately equal to 1. So the gas is what? The gas is ideal gas because the compressibility factor is equal to 1. Now, if you have the following parameters, given, let's say the temperature is 700, and that is it. Is a gas an ideal or real gas? Can somebody calculate that? Can somebody find the answer to that? Be very fast, please. Can you calculate that? Be very fast. My time is very close. Can somebody find an answer to that? PV divided by RT.
Sir, it is given big numbers
What's
because the pressure is 700 and not the temperature.
Yes, pressure times volume times the volume. 700 times the volume, 22.4 is equal to 15680 divided by what? Divided by 8.314 is equal to that. Divided by what again? Divided by temperature. Divided by 273. So the answer is equal to what? 6908. So can the gas be said to be ideal? Therefore,
No.
the gas is a real gas. So it's a real gas and not ideal gas. So based on the compressibility factor, you can know. So test yourself, under what condition can real gas obey the gas law? You know that at low watt and at high watt, at high temperature, low pressure. Calculate the compressibility factor of the gas. We have already done that. Based on compressibility factor, state which of the following gas is a real or ideal gas. So 1.4 is a real gas, 2.6 is a real gas, 1.0 is an ideal gas, and the other one is a real gas. So you can see that assignment, what account for the deviation of real gas from ideal behavior? State the two major kinetic theory that fails when the deviation from ideal gas is observed. And what is it? That the two major kinetic theories that gas has, the volume of a gas is not negligible. And two, there's attraction between gas molecule. Under what condition can the compressibility factor of a real gas approach unity? That will be low pressure and high temperature. So that is what you can see there. The need for real gas equation, then the van der Waals equation. Firstly, the volume of a molecule is by no means negligible and cannot be ignored under all conditions. We cannot say that volume is negligible, just like the kinetic theory assumes. Secondly, there exists intermolecular interaction between molecules at close distance. Van der Waals modified the ideal gas equation by taking into account the above shortcomings. Two corrections were applied considering the fact that one, the molecule of a real gas have a definite volume. So, and two, the pressure exerted as a result of the number of molecules striking the wall and attracting a molecule from behind. There's also a pressure exerted there. So Van der Waals equation, Van der Waals realized that the molecule of a gas have definite volume. Therefore, the entire volume of the container is not available for the free movement of the gas molecule. The volume available for the motion of the molecule can now be given as what? V minus NP, NB. P is known as a co-volume. So actually, and the pressure is actually higher. I will not take you to read all this in, but I'll take you straight to Van der Waals equation. So, and this is the Van der Waals equation. The actual volume is now given as V minus NB. And then the corrected pressure is P all over AN squared all over B squared. And so N is a constant, N and A is a what you call Van der Waals constant. A and B are called Van der Waals constant. So for 1 mole, the volume V is equal to, for 1 mole, the molar volume is now V. And we have the molar volume substituted here. What is molar volume? Molar volume is a volume occupied by 1 mole of a gas. The volume occupied by 1 mole of a gas is called molar volume. So that is what we see there So significance of the van der Waals equation. The van der Waals equation is important. It's very important equation, and it's applicable over a wide range of pressure, volume, and temperature data. The quantity A and B are called the van der Waals constant. B is a measure of the molecular size, and A is related to intermolecular interaction. So B is a measure of the molecular size because V is concerned with volume, and A is related to intermolecular interaction, that is due to pressure. B increases as the size of the molecule increases, whereas A has large value for an easily compressible gas. So take note of that, large value of the van der Waals constant, A, when the gas can easily be compressible. So van der Waals equation, B negligible. So it's the same thing here. So from here, we can calculate, just note, you may not actually be interested in this derivation for now, but just note that this is what the pressure times the molar volume of a gas all over RT will be 1 minus this. That is the actual compressibility factor for real gases. But for ideal gases, it is PV all over RT is equal to 1. So take note of that. And next week, we will review this before we continue. But the PowerPoint will be available on the site. So by next week, we will start with where we end, so that I will have to attend another class. But if there's any question, you can quickly ask, just 1 or 2 questions.
Okay, sir, where are you going to submit your assignment and when?
I mean the TMA or the
No,
assignment at this year?
Yes.
No, the TMA just finished all assignment for you. So this one is for your personal understanding.
All right. Thank you.
So have a nice weekend till next Friday. We continue from where we stop.
Thank you.
So have a nice time.
Thank you, sir.